All right. Hello, everyone. It's our pleasure today to have Professor Brighten Godfrey from the University of Illinois at Urbana-Champaign with us today. Brighten received his Ph.D. at UC Berkeley a few years back, and his general area of interest is in network systems. He is currently an assistant professor at the Department of Computer Science at UIUC. He's received several awards for his efforts in these directions, including several Best Paper Awards, and in particular the IEEE Comms Society as well as Information Theory Society Joint Paper Award, as well as the NSF Career Award. So let's welcome Brighten Godfrey.
Thank you. Thanks so much for inviting me. I'm going to be telling you about our work today on data center networks, and in particular designing the topology of a data center network. Let me, I guess I could introduce myself a little bit. The research that I do generally often involves a mix of building real systems and understanding them with theory. We're doing some work with software-defined networks and verifying security and correctness properties of networks in SDN, and making the internet faster, working on low latency networking. And then the third thrust is this one that I'm talking about today, which is in data center networks. And I want to mention that this is work of a number of awesome students. Ankit Singla and Chiao Hong are PhD students that are both senior PhD students. They'll be graduating within the next 1 to 2 years, so look out for them. Chiao is actually on the market this year. Kyle Zhao is a master's student, and Sangeeta Jyothi is a new student that just joined the project. And we've collaborated with Alexandra Kola, who is a graph theorist and computer science theorist here at UIUC, and Lucien Papa, who was at HP Labs at the time. So a wonderful group of people to work with who actually did essentially all of the real work. Okay, and let me also say, while I'm in the full screen here, I actually can't see you all. So I think what I might do, if you can see it, let's see if I can do this might not be the best way to do it. Okay, well, I think I maybe can't put this in front. All right, I'll go back to the full screen here. Okay. Well, I can't see you, so if there are any questions, please do not hesitate to speak up. I'd love to keep this interactive. And as we go through it, if you have your questions at any time. You can see the full screen slides now?
Absolutely, yes.
Okay, great. Okay, so the starting point for this work is really this picture here, which is showing the increase in bandwidth inside Facebook's networks between March 2011 and May 2012. And they broke it down. They're not showing you, they're not revealing the exact numbers here, but they broke it down into several categories: ingress and egress to and from the internet, and intercluster. That's all traffic inside their internal network. That's not going out to some client on the internet. So what you can see here is that there's vastly more traffic and much faster growing traffic between machines in their data centers. And that's been a pretty big shift in how data centers operate. It used to be that a data center was, doing a database lookup and spitting out the answer back to the client. But now we have data centers that are supporting cloud computing and supporting big data analytics. And both of those result in much more traffic among servers. In particular, big data analytics, you might be running a MapReduce job that has to do a shuffle among 1,000 or hundreds or thousands of machines, and that's basically all-to-all traffic. It's not localized. if you're running a cloud, you actually pay a lot of money for the servers themselves. So you want to drive the server utilization as high as you can, which means you don't want to be restricted about where you place your job, right? You want to be able to use any server resource that's available, which has come to be known as agility. And to be able to do that, you need uniformly high throughput throughout the network, okay? There's a second goal we're going for in this work besides high throughput in the network, and that's flexible incremental expandability. So if you have a big network, you're going to be often replacing switches, upgrading to different types of switches, and incrementally building out over time. Facebook, another graph from Facebook showing their server footprint over time, one of their VPs said, we add capacity on a daily basis. So the need for incremental expansion is pretty significant, and if the network can help that, it's a good thing. It reduces upfront capital expenditure, so you don't have to build the entire network at one moment. There are some commercial products that expand server resources, but the networking problem has not been tackled as much. So why are today's networks not suitable for these two purposes of high throughput and incremental expandability? Well, we can look at kind of a traditional network. This is a traditional data center network that is, showing just a slice of it here, and it's very tree-like. Right, that's maybe the first thing you notice. You've got some border routers up at the top, just a couple of them, really big iron routers, maybe from Cisco. And there's a tree that goes down to the racks of switches at the bottom. Now, it's not a tree, actually. A tree, you only have one path between any 2 points in the tree. But it's a tree with some added redundancy, right? In case any link fails or any switch fails, you always have another path. Now, this is fine if all of your communication is local, but if your communication is global, because of agile placement of VMs or big data processing, basically you're going to have an immense bottleneck at the root. Because typically, in these typical traditional designs, the root is very oversubscribed. It has much less capacity than the servers can pump through it. So, an approach people have moved to is what's called the fat tree. Okay, actually, this is the fat tree. So the fat tree is, it looks, in some ways, it's similar to the structure that we just saw. It's very hierarchical, but it has even more capacity, even more redundancy. Okay, so if you look at this in particular, this example fat tree structure, there's 16 servers on the bottom, and at every level, all the way up, there's 16 links. What this paper was trying to do, this paper by Mohammed Al-Faris and his collaborators in SIGCOMM a few years ago, is kind of an influential paper because it said, look, we're moving to a world where we need much more capacity within data center networks, and we're not going to be able to use these monolithic big routers at the top. So let's build a network out of many wimpier components. And let's build a very high capacity network, in fact, out of wimpy components. That's what the fat tree does. So all of these links and switches can be, relatively inexpensive commodity switches, but you're going to use a lot of them. Okay. So this was an influential paper that kind of set the course of a lot of data center research over the last few years. Are you all still there?
Yep.
Good. Okay. So here's what a fat tree looks like with a few hundred nodes. And of course, it does involve expense, right? Building a network that's this large involves buying many components, lots of cables, lots of power. And it's not only expensive just in a static sense, the structures people have used to devise these networks are fairly constraining, and they limit your expansion. They give you coarse design points. So a hypercube, for example. A hypercube is a structure that's been proposed in data center networks, also been proposed in supercomputers. In fact, a lot of this work comes from supercomputers. You can build a hypercube with 2 to the k switches. Okay, so if you want to add 1 rack of servers, it's no longer going to be a hypercube. It's going to be something else. It means you're going to get uneven bandwidth or you're oversubscribing nodes, right? Fat trees, the 3-level fat trees as used in that SIGCOMM paper that I just cited, have even worse granularity here. If you look at the common port counts of switches you would buy, then you're talking about being able to build a data center with about 3,000 servers, about 8,000 servers, or about 27,000 servers, and those are your design points, nothing in between. Okay, so it's unclear how to maintain structure incrementally in these networks. Are you going to overutilize switches? Are you going to have uneven bandwidth or constrained bandwidth? You could leave ports free for later, of course, but then you wasted some investment. Okay, so these networks have been constraining. So the idea in this work is to forget about structure. Since structure is a problem, let's have no structure in the network at all. Let's build a network that is completely unstructured, a random graph. Okay, and that is what sets off this design, which we call Jellyfish, and the systems work that's necessary to get a completely unstructured network to operate. Okay, so what am I talking about here? Well, if we design a Jellyfish data center, we still have racks of servers as before. We still have top-of-rack switches as before. And the servers are still connected to their top-of-rack switches. But the top-of-rack switches are interconnected with each other randomly. Okay? So the switches form essentially uniform random interconnections. Okay? And by doing this, we now think of capacity as, instead of being a structured solid, it is a fluid. Okay? You pour in switches and links, and whatever you pour in increases the aggregate capacity of the network, and you don't need to worry about the particular structure. And as we'll see, there's a very real formal mathematical sense in which this is in fact what happens. So that's where the name Jellyfish came from, but it also actually happens to look a little bit like a jellyfish. So that's where the name of the project comes from. Okay, so one of our goals was flexibility, ease of construction and expansion. Let's start with that because that's actually the easier case to reason about. How do we build a Jellyfish network? Let's say we start with this network of switches, and we want to add another. And we've got 4 free ports on this switch. Well, we're going to pick a random link in the existing network, remove it, freeing up 2 ports, and then wire in the new one there. And then we have 2 more ports free, so we pick another random link, and freeing up 2 ports in the existing network and wire it in, and so on. Okay, so very simple random link swapping procedure. Same procedure for initial construction for incremental expansion. Same procedure, no matter if you're adding a switch that's like 24 ports or 64 ports, might be different than what you were adding before, it doesn't matter. Okay? That's how you build it. Okay, and you can actually quantify using a model that we used from a paper called Leg Up by Andy Curtis and Keshav and Lopez Ortiz, which was in Codex a few years ago. And they have a model for what's the cost of incrementally modifying a data center over time. And they actually built an optimizer that was using tree-like networks, close networks actually, they're called. And they didn't do a bad job of it, but they had chosen a traditional style network, right? So when you do as well as you can, basically, in a traditional style network, you get a network that's still much harder to incrementally expand than a Jellyfish network, because you've got to be leaving free capacity and you've got to be moving way more links around when things change. So 60% cheaper incremental expansion to build the same network in a trajectory over time. Okay, but now we come to a question, which is throughput. This was our other goal, to build a high capacity network. And you might imagine that by giving up on some structure in the network, building a completely unstructured graph, do we take a hit on throughput, on the capacity of the network? The answer, it turns out to be very interesting. The answer, here's a graph which is measuring throughput of the Jellyfish versus the fat tree design. Okay, on the x-axis is the size of the network. So we're just testing various size networks. On the y-axis is the number of servers that the network supports at full throughput. In other words, without the servers getting congested. So actually what we see here is that not only is the random network not worse, it's actually using identical equipment, the randomized network is 25% higher throughput with the same equipment. Okay? And it can be even better than that. That was kind of a relatively smaller test. An example on the VL2 topology, which is a newer design that is used and now deployed in Microsoft's Azure data centers, it's also a close style network similar to the fat tree, but has different link speeds, for example. Okay, we can rewire this using the designs that we've through our simulations of how to design a topology, rewire this in an intelligent way, where we take the top of rack switches, okay, and we connect those randomly to the other switches in the network, and similarly the aggregation layer and intermediate layer switches are uniformly randomly connected to each other. Okay, and in this case, what we see is, as the size of the network scales up along the x-axis, we get roughly 40% more servers than the VL2 design. So in other words, you take existing network, same equipment, rewire it, add some intelligent traffic engineering and routing that I'll talk about, and you have 40% higher throughput. I should say right now, a caveat is this does depend on the traffic matrix. Okay, and we're trying to test here with bad case traffic matrices, server-to-server permutation. Rack to rack is even worse. This is where one rack of servers sends all of its flows to another specific rack of servers, and then you get less path diversity. Still, in this case, it's beating, which we think is not at all a common case, it's beating VL2 by more than 20% in growing in size. All-to-all traffic, as an example, is easier to handle than random permutation. Okay, so this is a little bit counterintuitive that we can get a significant benefit in throughput by using a slightly radical, completely unstructured topology, which isn't like what anybody has built networks like before. Okay, so this is really just the beginning. We can ask a bunch of questions here about topology design. Okay, here's a network that's better than the random graph. How close is this to optimal? Is there something better? How does it compare to various other structures like hypercubes or B-cubes or dragonfly networks or any of the dozens of other designs? What happens if switches are heterogeneous? How then do we deal with designing topology? And what about kind of the systems design aspects, like getting performance consistency, or dealing with the spaghetti of cabling, or routing and congestion control without structure? There's lots of questions here, and we've pushed on a number of these, and we're pushing on a number more. What I am planning to discuss in a bit more detail today is two topics: dealing with the spaghetti of cabling and routing and congestion control without structure. But maybe I can just pause here and take a little break and see if there are any questions right now. Comments or questions while I take a drink of water.
I think we're good. Thanks.
Good? Okay. And can I ask a little bit, what's the background of the audience in terms of algorithms, graph theory, that kind of thing?
I think we're pretty well up on it. COM, control, graph,
okay.
randomized algorithm. We should be
okay.
good.
Definitions of graphs and basic algorithms. Okay, good.
Sure.
I thought you would be. So, so let me, before I get into those two systems design aspects, I'm going to take about 10 minutes or so here and talk about a little bit of the context and then a little bit of intuition for what's going on. Okay, so first the context. Why are we building random graphs now, and why are we discovering higher throughput networks now? Let me start with a quote. It is anticipated that the whole of the populous parts of the United States will, within 2 or 3 years, be covered with network like a spider's web. Can anybody guess the date of this quote?
1900.
1900, okay. Other guesses? Only one guess? Okay, it's actually 1848 from the London Anecdotes, and it was accompanied by this illustration on the right showing how the electric telegraph brings humanity together like a web. Kind of an evocative picture there. I'm not quite sure what's going on in the top half of that, but anyway, the point is that people have been designing communication networks for a very long time. And in fact, high throughput has been a goal, right? In the early days of the telegraph, capacity was precious. Network capacity was precious. And it was limited by geography at that time, and is today in wide area networks. Now, if we move to maybe the first time that we built a kind of complex network that was not related to geography, was probably the crossbar switch. So this is automatically switching between phone lines, okay? And so this is a n by n sort of design here, where we've got n inputs in rows, or n inputs in rows and m outputs in columns, or vice versa. And the crossbar basically produces a matching between these. And that's essentially what's going on inside a switching network, whether that's the guts of a router or a data center network, or a switching within a chip. This is basically trying to get high throughput between the inputs and the outputs. If you have a full n by n crossbar, it can match any traffic pattern, that is any pair of input-output pairs, as long as it's a matching, can be implemented in this network, right? So in other words, it's a full throughput network. What's called a non-blocking network. Your phone call is never going to have to wait unless it's because the other party is actually already talking to someone. Now, of course, the crossbar switch is very inefficient, right? You've got n inputs and n outputs, n squared components, right? You can see it here in the picture, n squared. So a few decades later, in 1952, Charles Close worked on a substantially more efficient design for a high throughput network for telephone switching. And that's where the name the Close network comes from. And basically what he designed was a staged network that uses these crossbars as components, but has only log n stages in order to be able to switch any input to any output. Okay, so there are many examples of close networks that fall into this general class. One is the Benish network, another is the fat tree, kind of close network. In the computer world, the first time we had interesting, relatively complex networks was in supercomputing. This is the Cray T3D, which is the first system to use a three-dimensional torus network. And in fact, there have been many designs used in supercomputers, hypercubes, torus, fat trees, that are all highly structured networks. Because in a supercomputer, you have to deal with, you're not running TCP, right? You're not running TCP in a supercomputer. You're dealing with memory references. That has to be very low latency. That has to be very reliable. You have to deal with deadlock, potentially, in the routing. You can't have large routing tables. So all of this means that you have very simple routing, and therefore a very regular structure of the graph. So what's different about the situation today? Well, one reason data centers are exciting for networking as a research area is that they're much more flexible, right? So we have vastly more flexible packet forwarding compared with supercomputers. Right? We basically can set up whatever paths we want, and we have especially more flexible routing and congestion control when we have software-defined networking, where we have a central controller that we can program how we like and push out instructions to the switches about what to do. So we don't need to modify the switching hardware in order to do interesting new designs for routing. Okay, so this is why I would say these kinds of structures can be explored now, whereas they couldn't have been explored before. Okay, so that means we can build a random graph, and we'll talk about the systems we need to actually carry that through. But first, let's talk about this question of intuition. Why do we get 40% higher throughput in some networks with a random graph? What's going on here? Now let's take this, just the simpler case of the fat tree. 25% more at the scale of a few thousand servers, and it's actually increasing. It's getting the advantage increasingly towards the random graph as you build a bigger network. What is going on there?
How we measure throughput? What is the definition of the throughput? So you have some traffic metrics?
Good. Yes. Thank you for asking that question. What is the definition of throughput? So the graph that I'm showing you right now is a packet level simulation of TCP. So this is basically the good put of the end-to-end, the sum overall end-to-end flows that's being pumped through this network. Okay, so this is a packet level simulation. That is for a specific traffic pattern where we've basically told specific source destination pairs to communicate, and that traffic pattern is a random matching. So every server is sending to one other random server and receiving from one other random server. Does that make sense?
Yes, yeah, but some of the flows might experience like different level, right? So some of the
That's right.
flows, yeah, okay, so
yes, absolutely. Now, when I show you, there's actually two types of results that I'm showing you. This is kind of the full package. It's a packet level simulation with routing and transport and everything. We can think about just the graph structure itself and think about, in a fluid flow model, how good is that graph? And I'll show you some of those results, and those will take care of fairness. In that case, we're solving a linear program that we feed into an optimizer that says maximize this flow subject to, it says maximize the minimum flow of any of the end-to-end connections. And then what we report is the throughput for the minimum. So basically, it's handling fairness. In the other graphs that I'm going to show you, not this one. But good question. Anyway, you have a general sense of how throughput is being measured now? Okay, good. All right. So let's talk about some intuition. If we fully utilize all the available capacity in the network, how many flows can we support? Well, the number of 1 gigabit flows is going to be the total capacity in the network divided by how much capacity each flow uses. Okay. In other words, that's the sum overall lengths of the capacity of the link divided by 1 gigabit times the mean path length. Okay?
Mm-hmm.
Because if I send a flow down that goes 2 hops, it's actually using twice as much resources as if I send it down 1 hop. So all else equal, if we're actually able to fully utilize the capacity of the network, our mission is to minimize average path length in order to maximize throughput. Let's look at an example, the fat tree versus the jellyfish random graph. And actually, so this is tractable. Let's look at a simpler example here with just 16 servers and 20 switches. Okay, so here's an origin node. Where can we get in 1 hop? Well, here's where we can get in 1 hop. Here's where we can reach in 2 hops, 3 hops, 4 hops, 5 hops. Okay, so in 5 hops, we can reach 4 out of the 16 servers in the fat tree, but 12 out of the 16 servers in the random graph. So what you might have seen there is that the set of who we can reach is expanding more quickly in the random graph. In fact, there's a technical definition of expander graphs that is exactly this. And a random graph is a good expander. It's just like if you know the 6 degrees of separation result in social networks, and it's not exactly 6, that's folklore, or the 6 degrees of Kevin Bacon. People are connected through short chains of friends because we have effectively a lot of random connections. Okay, same thing going on here. That random connections give you diversity, which makes you reach lots of. Oh, I'm having a little problem. Let me deal with something here. Okay, all right, I think we're good again. The random connections give you short paths. Okay, in fact, you can look inside at what's going on here inside the fat tree. It's a tree-like network, which means actually we could take almost all of the links in the fat tree and just remove them, and the path length would not change. What does that mean? Those links in the fat tree were useful for providing redundancy and extra capacity, but they were not useful for reducing path length. So there was a missed opportunity there, that if we were building all of those links, we could have had shorter paths. Okay, and this bears out if you look at larger networks. So this is 686 servers. Here's the distribution of path length for jellyfish and the fat tree. So you can see that actually nearly all of the paths in a tree-like network are the same length. They're almost all the worst case. In the random graph, they're shorter, and there's more of a diversity. Okay, so that's the intuition for what is driving down the path length and therefore driving up the throughput. And I should mention here that when you talk about a high throughput network a lot, you talk about high bisection bandwidth. Has any of you heard that term before, high bisection bandwidth?
Right.
You probably have. Okay. Bisection bandwidth turns out to be the wrong metric for throughput. It's an upper bound on throughput, but it's a loose upper bound. Okay. It doesn't say anything about path length effectively, right? So you can have 2 networks that have the same bisection bandwidth, the same throughput and different bisection bandwidth. And you can have one network that has higher throughput but lower bisection bandwidth than another. Okay? And I think there's some confusion here that comes about because of the max flow min cut theorem, that cuts are the duals of flows, right? So if you have a bisection bandwidth is a cut, so you would think that the worst case cut is the minimal cut is the worst case flow, right? We all know that. We learned that in algorithms. Except that is only true for single source destination pairs, single commodity flow. If you're talking about multi-commodity flow, which just means you have multiple TCP connections open, it's no longer true. There's a gap. There's a gap between the cut and the flow. Okay? So in other words, people should not be using bisection bandwidth to measure throughput, to measure the capacity of the network. It's the wrong metric. And we'll see one other example of that. Okay. Any questions right now? I've got, let's see, I've got about, I think about 20 minutes left, and I'll talk a little bit about routing and then a little bit about cabling. But I can take questions at any point.
So just a quick question. So if you need a good expansion property, why you need random graph? There are structural graphs that will good expanders, right? So what is the magic of using random graphs? Yeah.
Yes, good question. There are, and we have tested other expanders like Ramanujan graphs. Kauf's graphs are also pretty good. And some of them are within 1% of a random graph. Okay? So the main reason is flexibility. You can very easily incrementally expand a random graph and use essentially whatever equipment you want. Whereas the other expander graphs are very structured, right? And they're tailored to specific sizes and combinations of port counts and so on. So it's really the flexibility that the random graph gets you.
Basically, flexibility to dynamically change network, right? So
that's right, exactly. And it's also, it's not at all clear what the structure would buy you. If you had a structured network, right? Like, so there are deterministic structures for, you know, like the Ramanujan graph, for example. Why is that better? It's still complicated, right? It's not clear that that deterministic structure makes it any easier to do cabling or routing, for example. But yeah, but that's a great question. There are, in fact, graphs that are as good as the random graph. And in fact, there are graphs that are better than the random graph, a little bit. And those you get by brute force search, effectively, plus some intelligence. But again, the problem there is they're, you know, very specialized towards particular parameters. But that's an interesting story too that I'm not talking about today.
It's kind of wondering from system administration, they want to have some structure, right? You tell them that it will be connected random.
Right, right, yeah. So there's some fear that this induces. So I think what you tell people is, we have a nice new algorithm that that produces a very careful mathematical structure that optimizes throughput. And you don't say the word random. But you know what systems operators want is understandable structure. And I think actually the other networks that get you high throughput will, they're deterministic structure, but it's not going to be something that you can keep in your mind as easily as you can, let's say, a tree. Or the kind of bundles of lengths that you get with a fat tree. But this comes to the cabling problem, actually. So I'll talk a little bit more about cabling a little bit later. Is there another question right now?
I think we're fine.
Okay. All right, let's talk about routing. So this is something that I swept under the rug a little bit here, right? Because I said there's this intuition. If we fully utilize all available capacity, then this is, you know, this is what we need to do. All right. That's a big if. How do we actually fully utilize all the available capacity in the network? That's the job of routing or traffic engineering. Okay. How do we do that without structure? Actually, most of the routing techniques today that are used in data centers depend on the structure. Now, in theory, this is a multi-commodity flow problem. You plug it into, you know, if you could measure all of the traffic, and if you could solve this problem instantly, then you'd be good. You just plug it into Cplex or some other linear program solver. The problem is, you know, traffic is constantly changing. It's a big distributed problem. Even if you know what the traffic is, it could take minutes or hours to solve some of these flow problems optimally. And when you did, it might be hard to implement it in practice if there are lots of small subflows. So the first thing we looked at is, okay, let's see what works in practice. One thing is ECMP. ECMP is widely used today in data centers. It stands for equal cost multipath, and it basically means when you've got a bunch of paths that are the same length, like you do in the fat tree, you split your traffic randomly over those paths. You hash it. You hash the flows onto the various paths. Okay, does this work? Not very well. Not in the random graph because ECMP doesn't utilize the path diversity. Here's something that shows that. On the x-axis, we have links. Okay. On the y-axis, we have the number of distinct end-to-end paths that can use that link. Okay. And so if you look at the green and red lines here with ECMP, many of the links over on the left have either 0 or 1 or 2 paths that can use them. Not a lot of choice there. Okay, so basically some links are going to be underutilized because of our choice of paths. Now you'll see a way forward here is 8 shortest paths. So what 8 shortest paths does is we pick for each source destination pair the 8 paths which are shortest. So some of them are maybe 3 hops, and then you'll have a few that are 4 hops, something like that. Okay, and when we do this, we get a big boost in the path diversity, and this ends up working. So we can find the k shortest paths. We can use multi-path TCP, although that turns out to be not very necessary, honestly. And what we get is this graph here is showing the optimal throughput compared to the packet level simulation. And we get fairly close to the optimal with this solution. There is room for improvement here, and we've improved that somewhat later after these results that I've shown you. But this is getting 86 to 90% of optimal. And in fact, the graph I showed you, one other point is that TCP actually does pretty well in this case. You don't really need MPTCP. The graph I showed you before with 25% better throughput, this already includes all of that routing and congestion control overhead, right? So I wasn't sweeping anything under the rug there. All right, so that's a routing solution. Basically, you need more path diversity, and you can deploy it many ways. There's some research proposals. We think the easiest way is with software-defined networking with a centralized controller, and that's, in fact, the way we're going in our test bed that we're building now. Okay, the last thing I'll talk about for a few more minutes is cabling, and then I'll just wrap it up. All right, so cabling. You might have noticed that this jellyfish random graph bears more than a passing resemblance to a bowl of spaghetti. So that can be fairly difficult to deal with if you have to build a large network. So there are several cabling solutions I want to mention here. First of all, there are actually fewer cables than a traditional network because we get higher capacity with the same equipment, so you need less equipment. That's one point to keep in mind. Another point is that when you get into very large networks where the cabling actually matters, so I should say, actually, in moderate-sized networks, cabling is probably not a big deal, like a few thousand servers. If you get into larger networks, it becomes a bigger deal. But then you can actually aggregate. So you can organize the network into clusters, and yes, it's a random graph, but you can lay out the cables in big bundles, right, running between the clusters. Okay? And then there's this generic optimization that you can apply to any network, including fat trees with placing switches centrally. I'm not going to go into that right now. But this gets into a geometric problem, actually, for these larger networks, which is how many long cables do you need? Okay? You can imagine designing a random graph where, let's just imagine 2 separate clusters, okay? The nodes on the left and the nodes on the right, okay? We could design a network where there are no long cables, okay? So all of the links are within one cluster. Well, then our network is partitioned. That's not very good. Or we could design it with something that's kind of a vanilla random graph where there are some links within the clusters and some long cables across clusters. Or you could even design a network where all of the links are long cables going across these clusters. Okay? Now, the question is, how many long cables do we need? All right? So we can put these on the x-axis here and vary the number of long cables on the x-axis, and then look at the throughput in the network that results from those various designs. Okay? Is this clear so far?
Mm-hmm.
Okay. So the question is, what happens? Okay, what's it going to look like? What is that graph as a function of the number of cross-cluster links? Is it going to look like that? Is it going to look like that? Is it going to look like that? Who knows, right? And I will point out here that actually the bisection bandwidth is maximized at the center point, okay, when you have essentially a random network, and then the bisection bandwidth stays the same off to the right. Okay? So here's what happens. The network looks like this. The throughput looks like this, okay, which was not what we were expecting. There's basically two regimes here. Whoops. There's two regimes here.
Same as the John Kleinberg result. He has the result on how many long links do you need for shortest path routing in random graph.
No, it's not the same as that.
You get this concave effect in the exact same fashion.
Right. So that's also very interesting, but that's a different effect. What he's talking about there is actually the effective routing of localized greedy routing.
Right.
So there are some networks in which it's easier to find paths than others with only local information.
Mm-hmm.
In this case, we're assuming we have global information. So actually, all of John Kleinberg's networks in that model have high throughput here. They all have enough randomness, or I should say a wider range. Let's not go into the details. A wider range than his results have high throughput, but it's hard to find paths. So in the data center context, we can assume we know the entire network. So it's not about the difficulty of finding paths. We can assume we have optimal routing. It's just the question is, what does the structure itself support?
Right.
Okay.
No, I mean, if you put in enough long links, the paths exist. So whether you're thinking of global routing or whether you think of localized hop-by-hop routing, his question is, do the routes even exist? And
well, his question was, do they exist and can you find them locally?
Exactly.
Right?
So,
yeah.
But you can't find them if they don't exist.
That's true. That is true.
In other words, putting in enough long links ensures existence of the shorter paths, and that's essentially what you're exploiting, right?
Well, okay. So actually, in all of these networks, the path length is pretty similar. Okay. So even in the networks all the way on the left, they do have short paths, but there's a bottleneck. Right. So there are short paths. So this picture I think answers your question. There are two regimes here, right? One regime is on the left side where the throughput drops off, and there you have a bottleneck. Okay, and on the right you don't have a bottleneck. It's just about the total capacity. Okay, and I think if I go through the intuition here, and then I'll come back to your point. Okay, why does this shape this result appear that there's basically this long plateau where it doesn't matter how you build the network for throughput?
Right.
Okay, why does that happen? Let's say we've got these two clusters on the left and on the right. Okay, and we're trying to get from one server on the left to one server on the right. In the vanilla random graph, there's actually many, many different paths that we could take. Some of them zigzag back and forth. Some of them, jump around within one cluster and then go to the destination. Okay. Now, what happens as we shrink down the capacity, the size of the cut between these clusters? What happens? Well, some of those paths we can avoid. We can avoid the paths that zigzag back and forth between clusters, right? We can get rid of those. And we can make sure that we just take the routes that cross the cluster once, that use just one long link.
Mm-hmm.
But we do have to at least take one hop, right?
Right.
We still need one crossing. So what does that mean? That gives us some intuition. That means of all of the capacity we're using, if the average path length here is APL, 1 over APL of it has to be in the cut in order to support our full throughput, okay?
Mm-hmm.
So, for example, if our path length on average is 3, then throughput should drop when less than roughly 1/3 of the capacity crosses the cut, okay? So that's what's going on here. From that intuition, we can actually get upper bounds on the throughput of any network that match pretty closely, okay, with the observed throughput. And the red and the blue are just two different combinations of parameters, okay? And in a special case, we can actually get constant factor matching lower bounds as well, explaining why this effect happens, and that the drop point is 1 over the average path length. What are the takeaway points here? Okay, and this gets to the point, your question, okay? In a minute, it'll get to your question. The intuition is here, there's 2 regimes of throughput. One of them is dominated by the sparsest cut, okay? And this is the kind of thing that bisection bandwidth measures. It's a slightly different definition, but don't worry about that. Basically, it's a cut metric, okay? But at some point, the cut no longer becomes the limiting factor, okay? Then we get this plateau, and the limiting factor is something different. It's not the bisection bandwidth. It's the total capacity in the network divided by the average path length. So in this regime, capacity behaves as a fluid, okay? You can basically push around your flows how you like because there's a lot of diversity in the paths you can choose. It doesn't matter too much. You have a lot of choice in where the flows go, so you can use whatever capacity is there. Okay? So, in other words, getting high throughput here is really a combination of 2 things. You don't want bottlenecks on the left, and on the right, you want short paths and lots of total capacity, right? So, random graphs, now connect this to the Kleinberg model. Random graphs have very short paths. The big difference, as I said before, with the Kleinberg model is he was looking at something more, even more difficult, which was not only does the graph have a short path, can you find it, right? So I think there was, in fact, a regime in his model where you don't even have short paths, and then you would get low throughput. There's another regime in his model where you have short paths, but you can't find them. Right. And if we tested those graphs, we would get high throughput. Because here we're assuming a data center network. It's not so big. You can see all of the switches, and you can do something that's close to optimal in terms of routing. But that's a good question. Okay, so takeaway points. What does this mean? Well, one thing it means is that you could imagine, well, what should we do with high capacity versus low capacity switches? Maybe we want to cluster all of the super high capacity switches together and create some sort of high capacity backbone. No, you don't have to do that. You don't have to cluster them. It also means that bisection bandwidth is a poor predictor of performance. Bisection bandwidth would not have explained this effect, and there's other interesting effects that it does not explain. So basically, you should not be using bisection bandwidth to measure throughput. which is good because it's actually NP complete to compute bisection bandwidth anyway, so it's a pretty horrible metric for throughput. It also means that cables can be localized. Okay, so you can basically divide the network into clusters, right, and reduce the number of cables across clusters, and correspondingly increase the number of cables within clusters. And this reduces the cost of your network, it reduces the cabling complexity, and it doesn't substantially reduce throughput. So those are 3 takeaways from there. And then I have a few slides to conclude, so maybe I'll just wrap up and then, so I'm all done and then I can take questions. So we're building a Jellyfish network now, and we have a test bed that has about 700 ports that we can slice up, and switch ports we can slice up and use with SDN, and we're cabling it up randomly in the lab. And actually a lot of the interesting work is in high throughput routing, even in unstructured networks. So we did pretty well in what I showed you, but there's some questions about how to implement that, how to deal with it if you have a dynamic situation. Can you do even better? Can you get closer to optimal? Can you optimize for particular applications? And then you can think about things like, well, how does this new topology change how you place applications in the network or VMs? Can you optimize that even more and get up to the application? Okay, so if you're interested in more of this, there's some papers available online. The first paper was in NSDI 2012, last year. There's a newer paper that's under submission, but the manuscript's freely available on my webpage and on archive. And there's one more paper in the works that's digging into this question of what should the metric for throughput be? Bisection bandwidth or something else, and how do a variety of networks compare on that metric? So that's in the works. I'd like to acknowledge generous support from Cisco and NSF for this work. And just to conclude, I think a takeaway point here is when we're building systems, there's often a trade-off. We have multiple objectives and there are tricky trade-offs. And it turns out in this case, for these 2 objectives, high throughput and easy expandability, it turns out that there's basically one network that satisfies both of these about as well as you can do, which is random graphs. So we think this is a much more flexible model for building networks that's pretty promising for future data centers. Okay, that's all. Thanks so much, and thanks for your attention. I can take some questions.
Thank you.